StarDrop's Metabolism module uses quantum mechanical methods to predict the metabolism of compounds by the major Phase 1 and Phase 2 routes for metabolism: cytochrome P450, aldehyde oxidase, flavin-containing monooxygenase, sulfotransferase, and UDP-glucoronosyltransferase. The which enzyme output shows which enzyme families are most likely to metabolize the molecule. For codeine, the Phase 2 enzymes, UGT or SALT, are likely to be important, as well as cytochrome P450. The output from the which P450 model shows that the 3A4 and 2D6 P450 isoforms are most likely to contribute to the metabolism of this compound. The predicted regioselectivity of metabolism for these major enzymes and isoforms is summarized above. Here we can see that UGT is predicted to glucuronidate codeine on the nitrogen and hydroxyl groups. For 3A4 we primarily expect to see demethylation at the nitrogen and the methoxy groups, while all of the 2D6 metabolism would occur through cleavage of the methoxy group. Hovering over a predicted site of metabolism shows the corresponding metabolite. We expect esomeprazole to be metabolized by the 3A4 and 2C19 P450 isoforms, and a more complex regioselectivity map is shown. In addition to the regioselectivity, the metabolic landscape gives a measure of the vulnerability of each site to metabolism by CYP3A4 in absolute terms. This provides valuable information to guide the optimization of compounds to improve metabolic stability. In the metabolic landscape, we can see that esomeprazole has two highly labile sites. Hover over the histogram bars to see the sites highlighted in the regioselectivity map. Blocking either one of these sites is likely to result in metabolic switching to metabolism at the other site, with little change in the overall rate of metabolism. This indicates that it will probably be necessary to block both sites to have a significant impact on the rate of metabolism. A table of metabolites is shown at the bottom of the metabolism area. All of the predicted metabolites and associated data can be exported into a new dataset for further analysis. Their exact masses are calculated for comparison with the results of metabolite ID experiments. You can apply StarDrop's other predictive models to identify the potential for formation of active or toxic metabolites. You can also generate metabolic pathways, combining metabolism from multiple enzyme routes through two phases of metabolism. The pathway is displayed in a clear, intuitive way in card view. For dextromethorphan, P450-mediated metabolism will initially generate two observed metabolites. These will be further metabolized via a combination of P450, UGT, and SALT. When planning preclinical metabolism studies, it is important to select the species that will best represent the predicted human metabolism. In the case of falnidamol, the which enzyme model shows aldehyde oxidase is likely to be a major route of metabolism. Guinea pig and rhesus monkey exhibit similar aldehyde oxidase activity to humans and would therefore be appropriate species to evaluate the metabolism of falnidamol. Sildenafil is primarily metabolized by P450 through N-demethylation on the piperazine ring. StarDrop's preclinical P450 models show that rat, mouse, and dog studies should all identify metabolism at that site. However, there are a few other minor sites, all of which are highlighted in the dog models as secondary or tertiary sites of metabolism, and one is a primary site for mouse. Therefore, the combination of mouse and dog would be an appropriate selection to provide the coverage needed for the preclinical studies of sildenafil. For more information or to arrange a free, fully featured evaluation, visit our website or contact info@optibrium.com.